Yeah.
If we have d equal 3, distance equal 3,
Mm-hmm.
but then we have two very small errors of 2 qubits.
What do you mean by very small errors?
I mean, like very small rotations.
Right. Okay.
How bad do we do to correct it?
Sure. So so in that case, suppose we have u is equal to 1 plus epsilon u prime, and so we have this on, say, 2 qubits. So we'd have u tensor u, which you can write as 1 plus epsilon squared u prime tensor I plus I tensor u prime, sorry, plus epsilon here, plus something that's O of epsilon squared. And remember that I said that if you can correct the errors A and B, you can correct A plus B. And so you see these first 3 terms, well, this is a 1 qubit error, and this is a 1 qubit error. This is the identity, so it's a 0 qubit error. So we can correct all of those. Okay. Now this O of epsilon squared term is a u prime tensor u prime, and that's something that we might not be able to correct with a distance 3 code. But you see it's order epsilon squared, whereas the error before we started was O of epsilon. So that's another way of seeing the improvement that you get from our quantum error correction. Any other questions? Okay, so yeah, so what I wanted to do today was get started on fault tolerance. But before we really get into that, I first want to talk about the general question of doing, what we're going to have to do when we talk about fault tolerance is we're going to want to do gates on states that are encoded in a quantum error correcting code, right? And we're going to want to get back states that are encoded in the same quantum error correcting code. And that's already something that's kind of non-trivial. If you take a code word of a quantum code and you do some kind of arbitrary unitary on it, the thing you get out will probably not be in the same code, right? The code is some subspace of a bigger Hilbert space, and you could end up anywhere in that Hilbert space. So we'd like kind of methods of analyzing these operations to see just what's permissible. And doing that will also help us understand, when we do have these gates, what they do to the encoded states. So to start off with, we're going to think about, we want to think about gates that map stabilizer codes to stabilizer codes. Okay, and suppose we start out with some state psi that's in a stabilizer code. And so we know it's in a stabilizer code, so we know that m psi is equal to psi for all m in the stabilizer. Okay, and now we do some unitary on it. So now we have u psi. And we'd like it to be the case that u psi is also in the stabilizer code, right? So m u psi should be equal to u psi. So let's look at m u psi. We want this to be equal to u psi. So we need to move the m past the u somehow, right? In order to get rid of it, and then we can absorb it into the psi. But that's not quite going to work, right? Because u, we don't know too much about it yet. It might not commute with m. So what we want to do instead is we want to look at u m u dagger u psi. Okay, this is going to be something more like the right-hand side, because what I've done is I've okay, so the u dagger u cancels here, and we get u m psi, and this thing is equal to u psi. Okay, so what this is saying is that that if psi is in the stabilizer that consists of these things m, then u psi is in the stabilizer that consists of these things u, m, u dagger. So what we've done is we've mapped S to S prime, where S prime is the set of u, m, u dagger with m and S. Okay? Does that make sense? Okay. So what I wanted originally, in order for it to be the same stabilizer, was that u psi was still an eigenstate of m. But really, what's easier to show is that it's an eigenstate of u, m, u dagger. But here's something that's important. So in order for S to be equal to S prime, you don't actually need that m is equal to u, m, u dagger, although that would be sufficient. Right? All you need is that u, m, u dagger is some element of S. Right? It could be a different element. And that's kind of the key to the set of operations that we'll be dealing with. And so in particular, we're going to be interested in cases where if m is in the Pauli group, then u, m, u dagger is in the Pauli group as well. Okay? And so this condition defines something called the Clifford group. Okay? So the Clifford group has this property that, well, it doesn't necessarily, given a particular stabilizer code, it doesn't necessarily map that stabilizer code to the same stabilizer code, but it will always map it to some stabilizer code. Right? It'll map it to the stabilizer code S prime on the upper blackboard. Okay? Let's look at some examples of things that are in the Clifford group. So one example, of course, is elements of the Pauli group. So if we have u in Pn, then, and this could be n qubit Pauli group, of course, then we know that u, m, u dagger, well, either m is in the Pauli group too, so either u commutes with it or it anti-commutes with it. Right? And when we move it through, then the u and the u dagger will kill each other. So we're ending up with plus or minus m. Okay? And because the Pauli group has these global phases, plus or minus 1, plus or minus I, that means that, well, plus m is obviously in the Pauli group, and minus m is in the Pauli group as well. So this is telling us that the Pauli group is a subgroup of the Clifford group. Okay, so we have one class of things. But of course, this is a class that doesn't do what I said before. If it takes m to another Pauli, it'll be, well, it could be minus itself, but it won't be something really different. Right? And in particular, if we were interested in gates that preserve a stabilizer, you can't take m to minus m because they can't both be in the same stabilizer. Right? That would mean minus 1 is in the stabilizer. Okay, so there are luckily more general unitaries that have this property. So one example is the Hadamard transform. So suppose we have, now at this point it's hard to just write down some single generic equation like this. So let's work out, for Hadamard, it's just a 1 qubit thing. So we'll just work it out on the single qubit Paulis and see what happens. Okay. So if we take h, x, h dagger, well, you can multiply out the matrices. I'm not going to do it on the board. There's not much point in that. But what you find when you do this is you get z. Okay. And if you take h, z, h dagger, you get x. Now, actually, it's enough to look at x and z, because if I want to do it for y too, which I have to in order to satisfy this definition, well, I can expand y as I x times z. So this is I h x z h dagger. And then I can insert an h and h dagger here. I guess an h dagger h is what I want. That doesn't really matter since they're the same. And so I have I h x h dagger, which I already know is in the poly group. It's z. And h z h dagger, which I've already computed as x. And so I z x, that's minus y. Okay? So you see that indeed the Hadamard is in the Clifford group. So at this point, let me stop to make a couple of remarks about some things that are happening here. So first, I've already pointed out that it's sufficient just to look at the conjugation of x and z. And we know that if those work, then y also has to work, right? Because if we get polys here, the conjugation of y will be the product of those things, which is guaranteed to, again, be in the poly group. And more generally, if we're working on 2 qubits or 3 qubits or n qubits, that means we only have to look at the generators of the poly group. X, III, Z, III on single qubits. Okay? So that's nice. So instead of having to look at all 4 to the n elements of the poly group modulo phases, we only have to look at 2n such things. So the next thing is that this conjugation action is permuting the elements of the poly group, right? And in fact, it has to, right? Because it's an automorphism. You can easily get back by doing, well, if u takes m to m prime under conjugation, then u dagger will take m prime back to m. Okay? So it has to be invertible, so we can't have 2 images that are the same. It has to be some kind of permutation. And moreover, you can easily see that it has to preserve the commutation relations. So so suppose we have m and n in the poly group, and we calculate u m u dagger u n u dagger. Well, the u dagger u in the middle cancels, and then we get plus or minus, depending on whether m and n commute, u n m u dagger, and then we can insert the u dagger u again to get the original things. So you see that the images of m and n commute if and only if the images if and only if m and n commute. Okay. And so these are kind of some of the fundamental properties of the Clifford group. It's in fact this. Well, yeah. Okay. So so it will turn out, in fact, I'm not going to prove this, I don't think, but it turns out that you can get basically any permutation of the Clifford permutation of the poly group by conjugation of the Clifford group, provided it satisfies this constraint and independence. Okay. So questions so far? Okay. Yeah. Yeah.
So we're implementing like a unitary, we don't care if it maps to the same stabilizer as long as it maps to some other.
Well, so I'm not into fault tolerance yet. Okay. So when we do talk about fault tolerance, we do want it to map to the same stabilizer. But right now, I just want to think about the set of unitaries that could possibly be useful for this, right? And that's the Clifford group, right? If it's not mapping the stabilizer to a group of polys, then it's certainly not going to map it to the same group of polys. Yeah.
So how does this all work instead of qubits you have qubits?
It works the same way. So in fact, I don't have to change any of these definitions. I just say the Clifford group for qubit. So you have a different Pauli group for qubits, right, with the shift and the phase operators. And then the Clifford group is defined this way. And yeah, that's right. And for qubits, you have to be a little more careful to make sure you actually remember to put in the daggers. For qubits, if you take the dagger itself, generally. But for qubits, that's true, but for qubits, it's not. Other than that, it's really the same.
So you said any permutation of the Pauli group is in the Clifford group?
No. Anyone that is preserving independence of operators. Actually, even that is not really separate, but it has to preserve commutation relations. That's important. Okay. Any other questions? Okay. So let me write down a couple of other examples. So there's the pi over 4 phase rotation. This is a diagonal gate. Can write it as 1i. And this has the property that if you conjugate x, you get y. It's diagonal, so it'll commute with z. Whereas the Hadamard switched x and z, and it left y alone up to a phase, this one switches x and y. Right? Y is going to go back to, actually I think it's minus x in this case. Okay? And so if you think about the Bloch sphere, you see what we're doing here is we have the 3 axes, right? And we're doing reflections that switch them. And there's also one that rotates x, y to z, which you can get by taking the product of these two things. Okay? So then that's single qubit gates. So what about 2 qubit gates? Well, it turns out that the C0 gate is also a member of the Clifford group. So it's a 2 qubit gate, so we're going to have to look at not just x and z, but x on the first qubit, x on the second qubit, z on the first qubit, z on the second qubit. So there's 4 things we have to check. And, whoops. Turns out that xi goes to xx, ix goes to ix, zi goes to zi, and iz goes to zz. Okay? And again, I'm not going to actually do the matrix multiplication, but you can do it if you want and find that this is what you get. Okay? And it turns out that that these 3 operators, Hadamard, pi over 4, and C0, can generate the whole Clifford group. Even on n qubits. You could have C0s on arbitrary pairs of qubits. Then you can generate the whole Clifford group that way. Okay? Any questions? Okay, so one thing that's nice about these descriptions, well, certainly it's important if we want to manipulate stabilizers. I already kind of showed you that. But more than that, this is actually enough to completely describe the Cliffords up to a global phase. Oops. So, okay. So what do I mean by that? I mean, oh yeah, go ahead.
Is it efficient, the description of an element in Clifford, if I want to write it in generators, is it an efficient description? Do you need a lot?
Yes. So it turns out that you can, given any Clifford group operation, you can find the a circuit that will use the generators to create that Clifford using O of n squared Clifford of these gates. Actually, it's O of n squared over log n. Okay. And in fact, finding this decomposition can be done in a time that's like classical time, that's like O of n cubed. But in order for that to be meaningful, you have to be given the description of the first Clifford in an efficient way. And so the way you want to do that is by giving its conjugation action. Okay. And the reason that that's sufficient is for what I'm about to prove right now, which is that if you have two things, u and u prime, that have the same conjugation action, that means that u is equal to u prime up to some global phase. Okay? So if I have the conjugation action and I find some circuit, for instance, that creates the correct conjugation action, it will give me the unitary that I wanted up to some phase that is not physically meaningful. Okay? So how do I prove this? Well, the maybe one hint is that since we don't care about global phase, we should be talking about density matrices rather than states. And so clearly, up to global phase, it's sufficient to look at u rho u dagger, right? And rho is 2 to the n by 2 to the n matrix. So we can expand it in a basis for the 2 to the n by 2 to the n matrices, and the Pauli matrices form a basis. Okay? So we can write this as u times some sum of ai pi running over pi in the Pauli group, u dagger. And we can take the sum out. And we get u pi u dagger. Okay? And so therefore the conjugation action tells us uniquely what the image of u acting on a density matrix is. Okay? And you can go a bit further and actually figure out, if you really want to, what the description of u is in the usual 2 to the n by 2 to the n matrix form. Usually you don't really want to do that because this description in terms of conjugation action, as I mentioned, only you can specify it by just specifying 2 times n images, right? And now each one needs O of n bits because you have to have an n qubit Pauli as the image. But compare that to the size of the matrix, which is 2 to the n by 2 to the n, right? So the point is that this description in terms of generators is an efficient description in n, whereas the original 2 to the n by 2 to the n is an inefficient description. And this is something that's special for Clifford group elements, right? Obviously, you can't do this for an arbitrary unitary in the unitary group. There's just not enough room. But Cliffords are very special, and and they have this nice property that you have an efficient description of them. Okay? So there are questions so far.
Is it obvious why C naught and R pi performs on the Hadamard?
It's not particularly obvious. So for Hadamard and R pi over 4, it's pretty obvious why they generate the single qubit Clifford group, right? Because it's permutations of 3 elements, and you have 2 transpositions that you know that's going to work. For C naught, I mean, you can work through the kind of the 2 qubit case, and there's not that many cases, but I don't know of a really obvious, clear way of doing it. Probably the best way of proving this is still somewhat involved. It involves writing these things as symplectic matrices and then doing kind of row reduction tricks. But I don't know of a really nice, clean, elegant proof of that. Any other questions? Okay, so this efficiency of description that I was just talking about carries over to actually figuring out, say, composition, right? Because if you do U and then you do V, well, the product, U times V, will be in the Clifford group also. And you can figure out, I guess, well, let's do U first and then V. So the product would be V times U. And you can figure out what conjugation action it does by just applying it sequentially to the polys. So let me give you an example. Let's take this circuit. Let me make it a little bigger. So some of you may have seen this circuit before and so know what it does. But what I want to do is I want to work out, using this formalism that I've shown you, what it does as a Clifford group element. We know it has to be a Clifford group element because it has 3 C naughts in it. But what Clifford group element is it? Well, so what we have to do is we have to look at the 2 qubit polys. And see what happens to them after each C naught. So the first C naught is from qubit 1 to qubit 2. So we take xi to xx, and ix to ix, zi to zi, and iz to zz. Okay. The second one has the second qubit as a control. So when x is on the second qubit, okay, so like this one, ix is going to go to xx because this is now the control and this is the target. And similarly, this zi, the z is in the target, so it goes to zz. Is that clear? Okay, good. So now things like xx and zz are a little more complicated because we have to take them as the product. We only wrote down over there what happens to the generators, and so we have to write this as xi times ix. Okay, and so xi will go to xi because x is in target, and ix will go to xx, right? So we have xi times xx. The x on the first qubit cancels, and we're left with ix. Okay, and similarly here, the z on the second qubit is going to cancel, and so we get zi. Okay? And then the last C naught we do from the first qubit to the second qubit again. So this is ix. This becomes xi. This becomes iz. And this is zi. Okay? So this is the map that this gate does. And we can actually identify this in terms of things that you probably already know. which is, so look at what happens here. So x on the first qubit goes to x on the second qubit, and z on the first qubit goes to z on the second qubit. X on the second qubit goes to x on the first qubit, z on the second qubit goes to z on the first qubit. So in other words, we switched the first and second qubit. Right? We're just swapping these two qubits. Okay? And that is indeed what this little 3 C0 circuit does. Okay? So does everyone see how this works? Are there questions on this? Okay. Okay, so this type of trick is it shows that not only do you have an efficient description of a single Clifford group element, but that if you have a product, a circuit composed only of Clifford group elements, you can track the overall product of the circuit and figure out what Clifford the whole circuit does efficiently on a classical computer, right? Because all you have to do is track what happens to each of these 2n polys, and at each step you have to do, well, really it's only O of n things, because if you have a 2-qubit poly, you have to update kind of those two qubits for all of these O of n things. And so at each step, you're doing something efficient, and at the end, you get the overall action of this Clifford group operation. Okay? And there's no time you need to do anything exponential. So this is the first part of what's known as the Gottesman-Knill theorem. So the history there is that Matty Knill, who was lecturing earlier, was the first to observe this property that if you tracked the polys, under the conjugation action, you could get an efficient algorithm to track the poly group. I mean, to simulate Clifford group elements. And then I did what I'm going to show you in a moment, which is to extend that to when you make measurements as well, which is also quite helpful. So in particular, if a circuit starts with a stabilizer state, and consists only, so stabilizer state is just like a stabilizer code with 0 qubits. So it's a case where the encoded Hilbert space is just one state. And so you have a circuit consisting only of Clifford group elements and measurements of polys. By this I mean measuring the eigenvalues of polys plus classical control. There is an efficient classical simulation. Okay, so I've already showed you how to track unitaries. So let's see how we can track measurements. so now I'm going to do something that's a little bit different than what I was doing here. So in this case, I was tracking all of the polys. But now, in this case, I'm starting with a stabilizer state, right? So I'm saying I have a state that has a particular stabilizer, like it might be, all zeros, which has a stabilizer that just consists of all the z's. Okay? And so I only have to track the things in the stabilizer, right? That's what I was showing at the very beginning, that if you start with a state that has a particular stabilizer, and you do a Clifford group, then the elements of the new stabilizer are the conjugates under the unitary of the original stabilizer. So let's do that. So we have a state with stabilizer S. Okay. And what we want to do is we want to measure on it some poly M. Okay. So there's a couple of possibilities. So one possibility is that plus or minus m is actually in the stabilizer. Okay, so in that case, measuring m will give us a definite answer. It'll give us plus 1 or minus 1, depending on whether plus m is in the stabilizer or minus m is in the stabilizer. Okay, and then the state obviously doesn't change then. And the other possibility is that it's not. So in this case, we have because it's a stabilizer state, we've completely specified the stabilizer. We know that that in fact that m will anti-commute with n for some n in S. Okay. I don't want to prove that, but it's not too difficult. And so this is going to be very helpful to us. Okay, so when we measure the eigenvalue of m, we're either projecting on the plus m eigenvalue or the minus m eigenvalue. If we project on the plus m eigenvalue, we're doing this operator to the state. Okay, and n is in the stabilizer, so this is equal to this 1 plus m n psi, and m and n anti-commute. And so what this is saying is that this state is no longer sorry, maybe I should have done it the other way around. So if you look at this state here, you put in, well, let me do the whole argument. So suppose you want to see if this state is an eigenstate of n. My claim is that it's not. So how do I know that? Well, I can put an n in front of this, and this is a projector, so I can do it twice, right? So I'll get and I know that I plus m psi gives us sorry, I'm getting confused here. Yeah, I want to get that, but I've kind of arranged myself so it doesn't work out right. Anyway, let me not try to figure out exactly the right way. But the point is that I plus m is not an eigenstate of n, right? That if you apply n to the minus 1 thing, you get the plus 1 thing, which is clearly not the same. Maybe that's just the way to make the argument. Okay, so we have a new stabilizer S prime. For the new state. And we know that n is not in S prime. Okay? But we know something that is in S prime, which is m, because we've just projected on the plus 1 eigenstate. So we started to, if we decided to build the stabilizer, we know we can not include n, and we should include m. Now, what else can we include? Well, if we have, so suppose we have some n in S such that m and n commute. So now I claim that n is still an element of the stabilizer. So if we apply it to 1 plus m psi, well, now it is going to commute through this. Right? It commutes with m and commutes with I. So this is 1 plus m n psi. And that's, the n gets annihilated, so that's just 1 plus m psi. So what we have is that n is still in the new stabilizer. Okay? So this is telling us a lot. It's telling us that if we have the original stabilizer, we should eliminate all the things that anti-commute with the m that we're measuring, and keep the things that commute. Not enough space here. Okay.
We want the S prime to be a subset of S? Or?
No, that's the point. It can't be a subset of S, because we're taking something that's not in the stabilizer and adding it, and we're taking some stuff that is in the stabilizer and kicking them out. So I guess I didn't say this, but in order to have a stabilizer state, we have n qubits. We just want a single state. So it follows from the number of logical qubits I told you yesterday, which is that there should be n generators of the stabilizer. And so what we're going to do is we're going to kick one out and we're going to replace it with m. And then everything else stays. But how do we know that it's only one generator that commutes? That anti-commutes, right? It might be more. In fact, if you're given a set of generators, generally there will be more than one that anti-commutes. But suppose we have, okay, so let's call this particular one n0. Suppose we have some ni such that ni and m anti-commute. Well, then it implies that ni and 0 will commute with m. Why? Well, when we move n0 past m, we get one factor of minus 1. And when we move ni past, we get another factor of minus 1. So we get overall plus 1, and the whole thing commutes. Okay? Yeah?
I kind of lost the motivation now under this.
So, yeah, the motivation. So what I'm trying to prove is I'm trying to prove that theorem up there, that we have an efficient description when we do a Pauli measurement of what happens to the state. Okay? And so what I'm trying to do is I'm trying to find the new stabilizer after we make the measurement. Okay? So I showed you what happens if we project on the plus 1 eigenstate. Right? We replace this, we get the new stabilizer as follows. We kick out n0 and replace it with m. And then we keep everything that commutes with m. And in particular, we can put the generators in such a form that all but n0 commute. Right? Because we can replace ni with ni times n0. Okay? So there's only going to be one generator now that anti-commutes. We kick that out, we replace it with m, and then we're done. Okay? And the thing is that all of this can be done efficiently classically. Right? All you have to do is you have to check, you have to find one thing that anti-commutes, and then you replace all the other ones by taking the product. Okay? So that's the proof of the theorem.
So we only prove there exists a set of generators in which only one is anti-commute.
That's right. That's all we need, right? Because any set of generators is kind of equivalent for describing the stabilizer. And so we just need to keep track of one of them.
Whenever we have another element which anti-commits with m, we just multiply it by m.
By n0, that's right. Same question, or?
These are all generators? We know that we're not.
We know that there can only be n generators. That's right. Yeah, I haven't proven that to you, but it's not too hard. Yeah. Excellent question. So, so why are these gates interesting, right? I mean, what I've shown you is that there's a classical simulation. So we know that there can't be, if you want to run an algorithm that has an exponential speedup over classical computation, you can't just stick to the Clifford group gates. Well, that's true. And so this is telling us two things that are both interesting. So one is that if we want to run kind of a universal quantum system, or really any quantum algorithm that's, well, this could potentially be a polynomial speedup, but anything that's beyond that, we're going to have to use some gates outside of the Clifford group. So that's one thing we know. But the other thing is that there's some very interesting things that we can do with Clifford group gates, right? I mean, let's look at them. There's the Hadamard. There's C0. You can make Bell states this way. You can make the GHZ state. You can do non-locality tests with just Clifford group gates and Pauli measurements. You can also create quantum error correcting codes, right? I haven't exactly shown you this, but it kind of follows from stuff that I said, that any stabilizer code can be encoded using just Clifford group gates. Okay? This is a set of gates that really does have a lot of quantum behavior in it, but it doesn't capture all of quantum mechanics. Okay? But when we are doing any of those things, it means that we have a good classical algorithm to track what's going on. Okay? And that is very helpful if you want to do that. Yeah?
I have probably stupid question because I don't really have an intuition of. So if we do this, we can get a new stabilizer on the output. But why does it mean that we can do efficient classical simulation? I mean, how to connect the stabilizer that we have after action of something with real output, and how to understand.
Sure. Okay. Yeah. So so it depends on exactly what you want the output to be, right? So for a lot of purposes, it's enough to just say, well, we want to track the state, and at each point we give what the stabilizer is. Okay, and that's how we describe the state. Okay, but I agree that's maybe not too satisfying. What if you have a circuit where you start out with all zeros, you do a bunch of Clifford group gates, you do a bunch of measurements, and then at the end you want to know what the probability of a particular measurement outcome is? Well, you can do that too. So if you're measuring something that's in the stabilizer, or where minus m is in the stabilizer, you can figure out which one it is, whether it's plus or minus. That's, again, a linear algebra problem, it turns out. And then you know that the outcome on that particular measurement is plus 1 or minus 1. And suppose you're measuring something that's not in the stabilizer. Well, it follows from these arguments, you have to kind of flip the m and n. It's not difficult to do. I guess I didn't show it to you. But there's actually exactly a 50% chance of getting plus 1 and a 50% chance of getting minus 1. Okay? And you can understand that because here you see n0 is mapping you from the minus 1 eigenspace, so the minus projector to the plus projector. Okay? And n0 was in the stabilizer before. So if you take the norm of this, right? Well, you get the 1 plus m squared doesn't really matter, and you take the norm of this, where you're getting 1 minus m. So on the left hand side, you have the norm of this thing. The n0 gets squared; it cancels out, and so I'm saying that the norm of this is equal to the norm of this, without the n0. Okay. So the norm of the plus 1 projector is equal to the norm of the minus 1 projector. So they have the equal probability, a half. Yeah?
So are you assuming here that m is in the Paulis?
Yes. Yes, because that's right. I didn't write that here, but the theorem is about measurement of Pauli's. If you measure something that's outside of the Pauli's, no, this doesn't apply. For a couple of reasons. I mean, the commute or anti-commute doesn't necessarily hold true, and putting M into the new stabilizer, well, we're going to get something that doesn't have Pauli's in it. So, okay. Other questions? Okay. Oh yeah.
So it's basically the way that you keep track of this thing, of the evolution classically is just like, say you start with some initial state that you specify the stabilizer, and then you just follow the circuit, and then you just specify what's the final state stabilizer.
That's right. Yeah. And along the way, you can figure out the probabilities to the measurement outcomes, which is how you can do the classical control, because you figure out the classical bits that come out of these measurements, generating 50-50 when necessary, and then anything that happens later you can control based on those classical bits. Okay, so so let me do an example of this to show you how it works. And I'm going to do it with a circuit that should be pretty familiar. Well, actually, maybe I'm going to skip the example. So let me, because I want to get to some other stuff today. So as an exercise, if you want to practice doing this, try to analyze quantum teleportation using these techniques. Okay, that's another example of an interesting quantum circuit that only involves Clifford group gates. Right? You can make the Bell state with C0 and Hadamard. You can do the Bell measurement with C0 and Hadamard, Pauli measurements. And so this theorem should apply. Okay? So if you do that, you can kind of get a sense of how these different tricks work together to get something that you presumably already knew. But you can also use them in cases to get things you didn't know. That's why it's interesting. Okay. So so now I want to move on to fault tolerance. So fault tolerance, let me first talk about kind of the formal model that I want to use to think about fault tolerance. So what we're going to want to do is we're going to have some circuit, and it's going to have errors in it. So what does that mean? So I want to break up the circuit into a set of locations. So we're going to have prepare some gates, prepare some qubits, then we're going to do some gates. They don't have to be Clifford group gates. They can be other kinds of gates, and we're going to make some measurements, and we're supposed to get some outcome. Okay, and so what does it mean to have errors in this circuit? Well, what I want to do is I want to break up this circuit into a set of locations. Oh, I can use some of the colored chalk. And so each thing that happens is going to be a location. And we can even have locations where nothing happens, right? Where the qubit is just waiting. So we're going to have lots of different kinds of locations, right? We're going to have state preparation locations. We're going to have gate locations for all the different kinds of gates that we have in our circuit. We're going to have measurement locations. And like I said, we might have waiting locations as well. Okay? And so my model of fault tolerance is just going to be to think about this circuit model, and each location might fail. And I'm just going to assume that it fails with some probability. This is a simplification, and it's one you can relax if you want to have a better result, but it's good to analyze in this way first. So if the location fails, we say it's a fault, and it gets replaced by some CP map. We don't necessarily know ahead of time what that is going to do. And if not, then it does the appropriate action. Okay? So let's see. So this error model that I'm talking about now is called an independent stochastic error model. But that terminology is not really very important, I don't think. Okay, does everyone understand this basic model that we're considering? Okay, so the upshot is that when this probability p is small, most of the gates and most of the state preparation, most of the locations in our circuit will do what they're supposed to do. But a few of them, chosen at random, will not. Okay, and we don't know ahead of time which ones are going to fail, and we don't necessarily even know exactly how they're going to fail. Right, there could be many possibilities. We want to somehow design circuits that take that into account, that we don't know which gates are going to fail. So obviously, if a gate fails, that's going to introduce errors into our system. Right? But what's maybe not obvious is that we can get errors kind of spreading even when the gate is acting correctly. So why is that? Suppose we have a C0 gate. Suppose we have a C0 gate. And let's just assume for the moment that we're acting on the state 0, 0. Okay? Well, what comes out? Well, it should be 0, 0. That's straightforward. But suppose there's an error on the first qubit. And so it's instead of 0, 0, it's 1, 0. Well, what comes out now? Well, now we get 1, 1. Okay? The C0 did what it was supposed to do. But now instead of just having an error on the first qubit, we have an error on both qubits. The error is propagated forward along the C0. And similarly, suppose the initial state in the C0 was plus plus. Well, if you do a naught on plus, it stays plus, right? Plus is 0 plus 1. So we're supposed to get plus plus out. Now suppose there's an error on the second qubit, so it's the minus state instead. Well, if you do a naught on the minus state, you get a minus phase. Okay? But we only are doing that naught if the first qubit was 1. So if it started out 0 plus 1, then the 0 stays the same, but the 1 gets a phase of minus 1. So in other words, the first qubit has again become minus. So the phase error propagated backwards along the C0. Okay, so this is something that's different from classically. Classically, sure, you can have errors that propagate forward along gates, but you can't have them propagate backwards. That doesn't happen. The control bit stays the same. And you can do this as a manifestation of this thing here, these conjugation relations. Right? You see there the x is getting propagated forward, and the z is getting propagated backwards. Okay? Does everybody see that? Okay, so which part don't you see? You analyze. You understood this?
I understand the ones in the zeros.
The plus and the minus. Yeah. So the minus is 0 minus 1. If you do a naught to that, you get 1 minus 0. In other words, it's minus, a phase of minus that appears. So if we had a 0 up here, the C0 doesn't activate, so nothing happens. So it stays plus. It stays 0 and then minus. But if we had a 1 up here, it does activate, and the minus gives us a phase of minus 1. So we have 0. So the state that comes out is 0 minus minus 1 minus, which is minus minus. Sorry, maybe I could. I'm not going to write it down yet. You try writing it down. You'll see it. It's a simple calculation. Yeah.
I just didn't hear. What do you mean the error propagates backwards?
Yeah. So what I mean is that in this example, there's an error on the second qubit, the target qubit. We normally think of the C0 as acting from the control to the target. Okay? But what this shows is that at the end, you have errors on both qubits. So that's what I mean by propagating backwards. It's kind of the opposite to the direction we think of the C0 as acting. And the reason for that is that the C0 in the quantum case, actually acts in both directions. It's not a directional thing. I mean, it's directional. It's not symmetric between the two things, but it's each of them is acting on the other one. Okay. So so this is something that's potentially very bad for us when we design fault-tolerant protocols, right? Because even if we have an error that starts out just on 1 qubit, suppose we have an error correcting code. If an error occurs on 1 qubit, that's fine. We know how to deal with that, right? That's the whole point of the error correcting code. But then we do a C0, and the C0 is itself fine, and now we have a 2 qubit error, right? And maybe our code can't correct that. So that's a problem. So in order to deal with that, we want to use what's called transversal gates. So a transversal gate interacts. So we might have multiple code blocks, one or more. So what I mean by this is, like, if we're using a 7-qubit code, we might have 14 qubits. One logical qubit encoded in the first 7 qubits, and a second logical qubit encoded in the next 7 qubits. Okay? And then a transversal gate is going to be one that only interacts the ith qubit of each block with the ith qubit of other blocks. So in particular, we don't want to ever have a C0 gate between 2 qubits in the same block, because that can cause one error to propagate into 2 errors in a block. Now, if we do this, it is possible that an error can propagate from one block into another block. Right? We can't avoid the error propagation. If we start out with an error in one block, we'll have one error in the first block and one error in the second block. But that's okay, right? If each of them is a 7-qubit code, each of them can correct one error. So that's something that we can still handle. What we want to avoid is getting 2 errors in the same block of the code out of one fault. Yeah?
So this definition doesn't include single qubit.
It does, actually, because single qubit gates kind of satisfy it trivially. Right? In particular, they only interact the ith qubit of a block with itself. Okay? Any other questions? Okay, so let's keep that up there. Okay, so now let's look at the 7-qubit code and start to put all the stuff I've done today together to figure out some transversal gates for that code. So remember, the 7-qubit code has this stabilizer. Let me skip the tensor products. Save a little time. Okay, so suppose we have this state. Okay, have a code in a code word of the 7-qubit code. Now, let's first think about transversal single qubit gates, right? Those are automatically going to be transversal, so that's easier to deal with. And we want to find some Clifford group gates that map this stabilizer to itself under conjugation. Okay? So one thing to notice is that these x's up here have the same pattern as the z's down here. And so what that means is that if we do the Hadamard on all 7 qubits, well, this operator here becomes this one here. And this one down here becomes this one up here. All 3 of these get switched. The top 3 get switched with the bottom 3. Okay? So we've mapped the stabilizer of the 7-qubit code to itself. Right? And that means that the state after doing the transversal Hadamard is again a code word of the 7-qubit code. Okay? So that's good. It's transversal because it's a tensor product of single qubit gates, and it maps the code to itself. So what does it do? Well, so to do this, I want to go a little bit further. Oh, sorry, is a question? No. Okay, somebody just moving their arm, that's all. Okay, so to do this, I want to go a little bit further and look at this set N of S. Okay, so remember N of S was the set of things that commuted with everything in the stabilizer. Now it includes the stabilizer. Anything in the stabilizer commutes with itself, but it includes some things that are not in the stabilizer as well. And those things have to map code words to code words, right? Because they're Paulis that commute with everything in the stabilizer. They're like undetectable errors. But they're not in the stabilizer themselves, so they're doing something non-trivial. And in fact, it turns out we can identify them as logical Pauli operators. Pauli operators on the encoded qubits. So in the case of the 7-qubit code, for instance, so I like to write these with bars over them. Sorry for people in the back that might not be able to see at the bottom. But the logical x is just going to be the tensor product of all x's. And the logical z is the tensor product of all z's. Okay. Now, these are not unique representations, right? If you take this tensor product of all x's and multiply it by something in the stabilizer, you'll again get a Pauli that has the same action on code words. Okay, so it's another. These logical Paulis are actually cosets of the stabilizer, and these are different, and they can have different representatives of the coset, if you know group theory. Okay, so so by looking at this logical x and the logical z, we can understand what the transversal Hadamard does to the encoded state. Well, the transversal Hadamard will map the logical x, tensor product of 6 x's, into the logical z, the tensor product of 7 x's to 7 z's. So it maps x bar to z bar, and it maps z bar to x bar. And therefore, this tensor product does the logical Hadamard. The transversal Hadamard does the logical Hadamard. Okay? So I realize some of that was a little bit fast, but does everyone kind of get the idea of how I did that? Are there any questions? Yeah?
Sorry, what does code block mean?
The code block, yeah. So I mean that like for the 7-qubit code, we have n equals 7 physical qubits, but we could so that's one code block. And if we have 2 logical qubits, we can code one of them using 7 qubits, physical qubits, and another qubit using 7 different physical qubits. And so that's a second code block. Okay? So it's like a single realization of the code.
So what do you call this transversal?
Yeah. Okay. That'll be more obvious when I do C0 gates, which I guess I could do now. So so the next gate I want to consider is the transversal C0 gate. So that's going to be a 2-block thing. So I'm not going to draw all of them, but you have 7 qubits up here and 7 qubits down here, and we have to interact only the ith qubit with the ith qubit. So the first qubit goes to the first qubit, and the second qubit goes to the second qubit, the third qubit goes to the third qubit, and so on. Okay? And so this is transversal because it's kind of, if you set up, so if you imagine having the qubits of one block arranged like this, and the qubits of another block arranged like this, the gates that we're doing are orthogonal to kind of the direction of the code block. So that's in the sense with our transverse or transversal. Okay. So suppose for the 7-qubit code that I do this tensor product of 7 transversal C0, tensor product of 7 C0s. So is this going to be a valid operation or not? So now I have 2 code blocks. So I have actually a much bigger stabilizer, right? I have 2 copies of this. So first I have these 6 things tensor the identity, and then I have the identity on 7 qubits tensor these again. Okay? And suppose I do the C0s. Well, what's going to happen to these things? Well, if we look at first at these things, these generators, Z, tensor I's, well, the C0s will not do anything, right? Because Zi goes to Zi. So that's okay. They stay the same. They're still in the stabilizer. And similarly, I's and then tensor X's, they'll stay the same. But what about this? X, tensor product of X's, tensor I's. Well, that gets mapped to X, and then on the second block, it's again X. Right? It's the tensor product of 2 sets of 4 X's. That's none of the generators that we had. But it's the product of 2 generators. Right? It's the product of the generator here, X's tensor I, with I tensor X's. Okay? So it's something that is in the original stabilizer of these 2 blocks. It's just not one of the generators, right? So it wasn't necessary that we get generators, that we permute the generators. We just have to map the elements of the stabilizer to elements of the stabilizer. Okay? And similarly, the generators that look like I tensor Z's get mapped to 2 copies of themselves, Z, tensor Z, which is again in the product, which is again in the stabilizer, the product of 2 generators. Okay? So C0 is a valid transversal operation. Okay? And what does it do to the code words? Well, the logical X here, we'll have 2 logical X's now, right? I have X on the first block and X on the second block. And X on the first block is X's tensor I's. That gets mapped to X's tensor X's, which is X1 tensor X2. And X2 on the second block doesn't get changed. It just stays X2. Z on the first block doesn't get changed. Stays Z1. And Z on the second block gets all Z's tensor all Z's. So it's Z1, Z2. Okay? And this is, again, the logical C0, if you compare. Okay? So let me point out that in order for this to work, we didn't use properties specifically of the 7-qubit code. We used properties of CSS codes. Right? CSS codes all have this form where we have a bunch of X's up here and a bunch of Z's down here. And that's all I needed for that to be true. So this is true for any CSS code. This did use special properties of the 7-qubit code. In particular, it used the fact that the top code C1 was the same as the bottom code C2 for For general CSS code, that doesn't have to be true. Okay?
So for general CSS code, is the logical operator always X or Z string?
Yes. Yes. So for any stabilizer code, the logical polys will be tensor products of polys. For CSS code, you can always pick them to be all x's, the logical x's to be all x's, and the logical z's to be all z's.
Somehow I'm confused about the surface code. Somehow it's not membrane, but then maybe you can choose it as a membrane. I mean,
Sorry?
I mean, for surface code, it's just a single string, which is not.
No, but it is. I mean, in the usual. I mean, there are different forms of the surface code, but in the usual form, you do in fact choose the logical x's to be a tensor product of x's, because one of them is like a chain, one of them is a cochain, and that makes the x's and the z's work out right. There are other forms where you don't do it that way, but. Other questions? Okay, so for the 7-qubit code, we now have the logical Hadamard, we have the logical C0. There's one more generator for the Clifford group. What about that? So let's try that. So that's the pi over 4 rotation, which, remember, takes x to y. Takes z to z. So these three generators will stay themselves. X gets mapped to y. So we have, for instance, y, 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 y. Okay? Now, is that in the stabilizer? Well, yes, it is. Because if you take the product of this and this, you get y, 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 y. And similarly, this times this is y, y, and then y, y here. And so on. Okay? So this is also a valid, transversal gate. Okay? What does it do? Can anyone tell me? Logical x to logical y. Okay? So it seems like it could do the logical pi over 4 gate. It actually doesn't. That was a trap. But it's very close. Okay? So what it does is it takes the logical z goes to logical z. That's certainly true. And the logical x, well, x goes to 7 x's goes to 7 y's. But let's take the product of this x bar and the z bar. Well, y is I x z. Okay? And here we're taking the product of 4 of them. So we got the i's all, I to the 4th is 1, so that didn't matter. But here there's 7 of them. Okay? And so when you work that out, that means that we're not actually taking x to y, we're taking x to minus y. And so our pi over 4 doesn't do the logical pi over 4, it does the logical minus pi over 4. Okay, which is pi over 4 dagger. Okay. Now, that's not fundamentally a big difference, but it shows you, first of all, that you have to be careful sometimes about the signs. Mostly you don't have to when you're dealing with stabilizers. Mostly you can kind of just look what happens to the x, y, z's, and that everything will work out. But occasionally, if you want to know exactly what's going on, you really do have to pay attention to the signs. And the other thing it shows you, which might not have been obvious, is that when you do one of these transversal gates, the logical gate doesn't have to be the same as the physical gate that you're doing. Okay? In this case, it's a pretty similar gate. That doesn't have to be the case either. Okay, so but the good thing is that if we can do the pi over 4 dagger, we can also do the pi over 4 rotation. And so for the 7-qubit code, we have a set of generators. We have the Hadamard, we have the pi over 4, we have the C0 for the Clifford group. So that means we can do everything in the Clifford group. We don't have to check them all separately. So that's pretty good. For 7-qubit code, we have a whole big slew of fault-tolerant operations. Unfortunately, we also know from the, well, it's covered now, the Gottesman-Knill theorem, that this is not going to be a universal set of gates. Right? So we're going to need to do something outside the Clifford group. So you might say, okay, well, we just have to look harder. Maybe there's some transversal operations, some transversal gates that are not Clifford group gates. But it turns out not to be the case. For the 7-qubit code, it's exactly, the transversal gates are exactly the Clifford group gates. And in fact, there's a more general theorem about this. So it's a theorem by Eastin and Knill. And it says that for any quantum error correcting code, I don't know if you've seen this acronym before, quantum error correcting code. It's very common. The set of transversal gates, logical transversal gates, I should say this applies with distance at least 2. Set of logical gates which can be implemented transversally. Is a discrete group. In particular, it's a finite group. And what that means is that it cannot be a universal set of gates, right? Because a universal set of gates, you could be able to take products of them, that would be the group generated by those gates, and get arbitrarily close to any unitary. But there's infinitely many unitaries. To get arbitrarily close to any unitary, you need an infinite set. And so we're never going to be able to do that as a consequence of the Eastin-Knill theorem. We're never going to be able to do that with transversal gates. Okay? So what this means is that if we do want a universal set of fault-tolerant gates, we're going to need some new tricks. Okay? And I'll talk about some of those tomorrow, along with how to do fault-tolerant error correction and stuff like that. Okay, so let me give you an exercise. So there's 2 parts. So the first is to show that the transversal Hadamard is not a transversal gate. It's not a valid logical gate for the 5-qubit code. And the second part might be a little difficult, but I want you to find a single qubit Clifford group gate such that the tensor product of 5 U's is a valid transversal gate, valid logical gate. For the 5-qubit code. Okay? So, any questions? Yeah?
By this, do you also mean that the set of logical gates which are implementable transversely, they lie in the Clifford group?
By the Eastin-Knill theorem?
Yeah.
No, in fact, that's not the case. There are some codes, even stabilizer codes, which have non-Clifford transversal gates. But those codes will not also have all Clifford group gates as transversal gates. So you'll still end up getting only a finite group. Just to be a different finite group.
You don't
Well, I mean, for the 7-qubit code, for instance, that will be sufficient. We're going to just add one non-Clifford, non-transversal gate. But you don't have. But it turns out, in fact, that if you take the Clifford group plus any gate outside the Clifford group, that's a universal set. So you know that's not going to work transversally.
You're saying it's not possible to have a transversal non-Clifford gate if you have
The whole Clifford crunch. That's right. That's right.
So following up from that,
Mm-hmm.
would that set of gates, which would include non-Clifford gates, would that be efficient distinguishable or not?
I think the examples we have are, there's probably some level of open question there. I'm not sure we could. Maybe if you restrict to stabilizer codes, it could be proved. Because there you have some kind of limits on what the non-Clifford gates could be transversally. But for general codes, I'm pretty sure we don't know. Yep.
So is there a order restriction on the discrete group?
Not as part of this theorem. I mean, in practice, no. In fact, there's no order restriction because you can get rotations by pi, z rotations, pi over 2 to the n. There's some codes that have that transversally. So that could be arbitrary high order. Yeah.
So if something's not part of the group, does that mean that like it doesn't trigger stabilization?
Well, so what it does is it doesn't map polys to polys, okay? But it's still possible that it could map the code subspace to the code subspace. It just, you can't understand that by looking at what happens to the stabilizer. Or you can maybe, but it's much more difficult. Because the stabilizer will get mapped to non-polys, which might also happen to have the property that they have +1 eigenvalue for everything in the code. But it's much more difficult to analyze then.
So if it's like not a poly, you mean it's like, for example, a standard poly?
Yeah, for instance, yeah. Yeah.
Are there any finite groups that are larger than the Clifford group but still be classically simulated? For instance, like the normalizer or some subgroup of
There are, but they're not really interesting ones. So okay, the example that I just gave, where you have phase rotations by small angles, those are finite groups. They can be arbitrarily large, even on a single qubit. But they're just diagonal, so it's relatively straightforward to simulate them. The only other really interesting kind of non-abelian. Well, the only other group that I would say is a finite of comparable interest, finite group to the Clifford group, is the set of classical gates, which is clearly classically simulatable. I don't know of any others, but there might be some weird ones out there that we just haven't discovered. Any other questions? Okay. Oh, yeah.
Is there a reason why we choose the T gate as the non-Clifford gate usually?
Yeah, we'll talk about it tomorrow. Okay, thanks.